I'm going today to celebrate Nash's paper, 60 years of Nash's paper, right? So what I'm going to do is, first of all, correct some mistakes in my handwritten notes, because exactly in the statement of Nash's inequality, there is a typo, which was on the blackboard. Then when I tried to use it, I realized that there is a typo, and I changed, as you remember. But I see that there is a typo. So let me state Nash's inequality. I will do two things. So all I do today, essentially, will be about a paper of Nash, of John Nash, 1958. And there are two things in this paper. Okay, there are many things in this paper. The point of Nash was the following. He wrote down, he was interested in partial differential equation, in existence and regularity of solutions of parabolic and elliptic partial differential equations. And the point was to prove uniform bounds in order to prove existence for non-regular coefficients, only assuming boundedness of the coefficients from below and above. I will not do PDEs now because I'm on the lattice, but just to give you the context. Without assuming regularity, smoothness, and so on, which was the usual stuff at that time, it was an enormous step forward in understanding partial differential equations. And it's of course related, as parabolic and elliptic PDEs are related to diffusions. It's related to diffusions to actually all these things have probabilistic meanings. And what I'm going to do now to give you the two main parts of Nash's paper, to two main results, streamlined and not in the continuum, but on the lattice. In the continuum would be simpler, actually, so maybe I made a mistake. In the continuum, since differential calculus has good notation, everything is worked out. If you do differential calculus on the lattice, then you have to introduce more notation, and sometimes it's more clumsy somehow. But I'm doing random walk, so I do it on the lattice. So I stated yesterday a theorem, which is Nash's inequality. Nash's inequality, I used it, I applied it, but I didn't prove it, I only stated it. And okay, all the context, before I state Nash's inequality, let me tell you what the context of the paper is. So we are on ZD. Our spaces are LP on ZD with counting measure, and actually P equals 1, 2, and infinity will matter. We have jump rates, Px, I call it P sub Kx, which are jump rates for a random walk to jump from x to x plus k. These are greater than or equal to 0, finite, could be unbounded. I denoted, remember, I don't write again, S sub Kx, so Px is equal to S sub Kx plus V sub Kx, and this is my decomposition in symmetric and skew symmetric part. Note, I will denote a random walk. At some point I will take also the reversed one, so the P starred Kx will be the same with the minus here, right? And I denote the random walk xt and x starred t are random walks with these jump rates or those jump rates, right? And it's important to note that due to the divergence theory or double stochasticity, this random walk will keep counting measure as stationary measure. Forget about the random environment now, it's about deterministic. Someone gave me these coefficients, these jump rates, and I'm doing the random walk with these jump rates, right? So it's totally deterministic what I'm doing now. Later I come back to the random environment. So mind that the counting measure will be stationary, and I'm set in that space. And the first theorem was Nash's inequality, which I used already, and I will not use it in a different context. I just want to state again and prove it because it's such an important thing in the history of mathematics and in partial differential equations in general, that you are in a school, learn something classical, great thing. Some of you know Nash inequality. I think very few of you, one or two. So you learn something which is good, worth learning for sure, right? Now, Nash's inequality is the following. There exists a constant, and I call it lowercase c, CD, which is positive, where my convention is that lowercase constants will be, the emphasis will be that they are positive, uppercase constants will be, the emphasis will be that they are finite. Of course, all are finite and positive, but I want to emphasize what's the important thing, which is positive, such that for any f minus Laplacian f, and this is now the lattice Laplacian, is bounded below by this constant times the f L2 norm squared of this guy, and here was the mistake, d plus 2 over d, not over 2. Please correct the handwritten, correct the notes. This is a d, not a 2 as in the notes, right? Times f1 squared to the power minus 2 over d. And I said that the expression is homogeneous in f. If we multiply f by an a, you get the same, right? And when I said yesterday, then somebody noted that it couldn't be homogeneous with the wrong exponents, right? Good. Let's prove this thing. I've used it already. Let me prove it. Proof of Nash's inequality. If I find it. It's a very simple proof, actually. It's a very beautiful proof. It's a very beautiful proof. Here it is. Good. So I write down things in Fourier transform. Question?
Yes, can I ask a question about the beginning? The statement of the theorem. If xy is no more than a constant over t, it's clear
That followed from this. It was a consequence of this.
So if we just look at the diagonal heat kernel, ptxx, it's clear that you cannot have the weights too small, because otherwise you could stay in the same point. But is there an equality in which the weights are just bounded from below?
It's not easy to give lower bounds. It's absolutely not easy in this general context. That's also partly in the paper of Nash. Similar things are done. For this statement are not needed to be bounded from above, only from below. And not p's, mind, the ellipticity condition is that the sk x's are larger than an s, the lower star, which is positive, and at the moment I don't assume anything about an upper bound. In the next statement, the second one, I will have to assume some boundedness, which you will see later, but for this one, by the way, it's stupid what I'm saying, because here you don't even see the random walk, because this is with the Laplacian. But yes, that was nonsense. I will need this later. But in the application, I used the same thing with the symmetric part of the random walk, and the symmetric part of the random walk, due to this, is bounded below. I mean, the operator is bounded below by constant times the Laplacian. And that's what I used, right? Yes, I shouldn't have done it. For the Nash inequality, you don't need anything like that because it's just an abstract statement. It's about Laplacian, and it's a statement about ordinary symmetric random walk, if you wish, right? But a subtle one, a subtle one. Okay, so let me prove this. Let me prove this. I denote, okay, I use Fourier transform and note that f minus Laplacian f, if you write this in Fourier transform, this is scalar product on zd, so that means sum over x and so on and so on. If you write down things in Fourier transform by, I don't know, Parseval formula, you get the following expression. You get 1 over 2 pi to the power d integral in the cube minus pi d, because that's the domain of the Fourier variable. When you take Fourier transform on the lattice, then this is the domain of the Fourier variable, which I will denote theta, say. Is it clear, right? And the expression you get is f hat theta squared times d hat theta d theta, where d hat theta is the Fourier transform of the Laplacian, which you had seen already once. I write it down again. D hat theta is equal to sum over j from 1 to dimension of 1 minus cosine of theta j. So that's just the Fourier transform or diagonalization of this. Good. Now I do the following. I have on, okay. Now I write f norm squared in the same way. That will be 1 over 2 pi to the power d integral on the same cube of f theta hat absolute value squared v theta. You don't have operator in between, which is thus Parseval's formula, right? L2 here and there are the same. And I choose a beta, choose beta between 0 and pi, and we will optimize in the end according to the choice of this beta. And I write this integral. Let me write this. So I integrate and normalize the integral. Let me write it like an integral. Okay, I'll show you how I write it. Integral like that. This means that the normalized integral, right? I have theta and L infinity norm of theta be less than beta, the same integral plus integral theta infinity norm larger than or equal, doesn't matter, theta, beta. The same thing. That's just division, or that's just straightforward. Which is, and now I do the following, which is less than or equal to, I'm not so good as others here to use the blackboard, I use too much space. Anyway, this is less than or equal to, let's see, the first one, when this is less than beta, I just in a trivial way, I dominate it, I take an upper bound by dominating by the L infinity norm of this function. So this will be less than or equal to 2 beta to the power d by, say, 2 pi to the power d times f hat infinity squared. Is it clear? So this is the box in which, this is the volume of the box in which I integrate. I dominate this by its supremum. Okay, and in the other case, I write, this is a subtle thing. Note, here I make a note that what do I need? That d hat theta divided by theta infinity norm squared is bounded by above and by below. Is bounded by two constants. Say, probably I should be very careful about C prime. I don't know, about C and the capital C. Why? Because the only problematic point is theta equals 0. But if you look at this function, at theta equals 0, this is like constant times theta norm squared. And you compute the constant explicitly. You can compute the constant, and you find this lower and upper bounds. Right? I will need only, probably I will need that the infimum is positive. I will need only the lower bound, but you also have an upper bound. So in the second place, I get 1 over 2 pi to the power d, which I don't have because I use this other notation. I have some constant, and this is what I will call a C prime. I will have C prime, C second, and so on, various constants going on. In the end, I will find this one, divided by give me a second. Yes. Divided by beta star, yes, it's right, times integral from minus pi times this integral of f squared, f theta squared, d theta d theta. Right? How did I get it? I bounded these things by, so I multiplied by this, multiplied by theta squared, I divided by this. I wrote theta squared divided by d theta multiplied by d theta and divided by theta squared. And the second theta squared is bounded by this guy. One of these is left there, and this is and the fraction is bounded by that. It's a very simple thing. And also note that this guy is less than or equal to f1, the L1 norm of this guy squared. The L infinity norm of the Fourier transform is bounded by the L1 norm of the very simple, right? So altogether what we get is that, and here I had, okay, I did another thing, but I changed this second integral to the integral over all, right? Yes. Good. And now I do the following. I collect things. I will get f2 norm squared is less than some constant comes here, some constant, let me call C double prime. I have a beta to the D. I have an F1 squared, and here I have another constant which I will call C triple, which contains all the pi's and everything. And I have beta to the minus 2, and I have F minus Laplacian F. So I have a relation of these, and this is valid for all betas. And I will stop now. I will not finish the proof because the rest is just straightforward. The ideas, you have seen the ideas, which are Fourier transform and noticing something interesting. Now optimize for beta. This is true for any beta. Is a simple expression which contains a beta to the d and contains a beta to the minus 2. Optimize for beta, and you get the result. You have to be a little bit careful, because when you optimize for beta, the optimum value may be, we had a constraint for beta. The optimal value may be within this interval, and then you get exactly what you need. So if you optimize with respect to beta, you get exactly the expression. So if you optimize this for beta, the right-hand side for beta, you get exactly the expression in the theorem. But one issue may arise, that your optimal beta is outside this interval. But if your optimal beta is outside this interval, you see in my notes what you do, it's even simpler. Right? So, and that's the proof. And so from here you have Nash's inequality, which is one of the gems of PDE theory or analysis. It's well known, of course, but at that time it was an absolutely ingenious innovation. Okay, let me not delete this one. And now I come to another element of Nash's paper, which I will use for my own. This one I used already, and I will use it again and again later. But I come to another element of Nash's paper, which I call Nash moment bound, which is less known, by the way. I don't know why. And which will be of paramount importance. And I tell you why it will be of paramount importance in our further explorations. Now, in order to state Nash, okay, so Nash theorem. No, before stating the theorem, I have to do some manipulations. You recall that this V sub k from Helmholtz's theorem could be written in terms of a height function. Let me assume, because there are some conditions under which you have the height function or the stream tensor, let me assume that there exists H sub KL X with the symmetries. Remember the symmetries. H sub LK equals minus H sub KL, and H sub K minus KL of X plus K equals minus h sub klx. And from there you build up other identities. And this tells you that h sub k is L is actually, it's a function on the oriented plaquettes of your lattice. So this will, okay, I told you already, let me not waste time on this. So this is a function on the oriented plaquettes of the lattice, right? And I assume that such a thing exists, such that v sub k of x is equal to sum over L, nearest neighbor, h sub k L x. And one of my theorems I proved, or I gave you hint of the proof time ago, was that in the random case when v is stationary and L2, then indeed it is the case. And in general, in 2 dimensions, it's always the case in higher than 2 dimensions with some constraint on the increase of the v's, but let me not care about that now. I assume, right, that it comes like that. And then the theorem is the following. The theorem from Nash, so let me call it Nash heat kernel upper bound. No, sorry, that's what, no, this is a Nash moment bound. I'm confusing now things. This is the Nash moment bound. Right? Is the following, that assume, and now it's to the question of Asaf about upper bounds, in Nash's paper is the following done. Assume, now I also have, so S sub k x is bounded below by S star, this is old, but I also assume an upper bound, a finite upper bound, and assume h sub k L x. I have to put absolute values here because h may be positive or negative. S is always positive. Is bounded from above by something I call, say, h starred, which is finite. So what is assumed now indeed that 1, the jump rates are bounded above. Second, the height function or stream tensor from which v comes, from which the antisymmetric part comes as a curl, is also bounded above. Mind, in my case, this is not, I said that, in my case, in my random walking random environment, I don't have this. I have another type of L2 bound, which is much, much weaker than this. But let me show you first what Nash did. Then, under these conditions, there exists a constant yes, so this assumes there exists a constant which depends only on dimension and is S lower bound, S upper bound, and H upper bound, such that expected value starting from 0 doesn't matter because I have these uniform bounds. So if I go start from another point, it will, the same bounds will hold. Expected value of absolute value of xt is less than or equal to this constant times square root of t. This is a miracle. This is an absolute miracle because without much assumption, it tells you that at least as order, it can't be worse than diffusive. This doesn't tell you anything about essentially anything. So you can have anti-symmetric part, but there is, of course, this constraint will tell you something about the anti-symmetric part. So this somehow tells you that the random walker can't go way too fast. Right? So this is one theorem I am going to prove. This is Nash's original theorem. But let me go to my context another theorem. Assume, so this is in my paper. So this is 2018 or 18 to appear in the Annals of Probability. Is the following. Assume the lower bounds, that indeed skx is bounded below. I need the ellipticity, unfortunately, which is positive. And assume that, okay, I should have, the context is different. Now I am in the random environment context. In the random environment context. That means that these guys are random, stationary, ergodic, right? Assume that there is a lower bound almost surely, and assume that integral over my random space of sk to the power 2 plus epsilon d pi is finite. Call it, so the maximum over k, call it, say, S upper bound is finite, and the maximum over k and l of integral on omega of hkl, this depends on omega because we are in the random case, omega to the power 2 plus epsilon d pi, call it h upper star, is finite. So mind, I don't assume boundedness. I assume that these random coefficients, as random coefficients, are 2 plus epsilon integrable. Then there exists a constant depending only on dimension on S lower bound, S upper bound, H upper bound. But mind that these are now different than in Nash's theorem. Such that for almost all pi, almost all omegas, mind, for almost all random environment, there exists a T starred, call it T star, depending possibly on the omega, which is finite, such that expected value quenched with the environment omega of xt absolute value is less than this c times square root of t, assuming if t is larger than t star. Then there is a finite late time, which might be long if the environment is very unpleasant, but anyway, a finite late time after which Nash's bound is settled. Question?
Do you have tail bounds for this talk?
Tail bounds for the walk.
For this talk, so that this talk. I mean, some moment bounds for this talk.
For xt, you mean?
No, for this talk.
Ah, for t star. No, because as you will see, t star comes from an ergodic theorem, for an ergodic argument that there is some convergence, and after some t star, the convergent sequence is closer than something. No way. If you don't assume, okay, it's very, very intricate. No way. No way for tailbound. Yeah?
Do you have any probabilistic interpretation of H?
Of H? Yes. I have, okay, probabilistic interpretation. Let me go. Let me give you the diffusion context. Let me give you the diffusion context because that explains itself better. Got it? Let me give you the diffusion context. The diffusion context is the following, that I have a diffusion in an environment, an inhomogeneous diffusion, for which the infinitesimal generator, so the xt diffusion in Rd, right, with the infinitesimal generator equal to, okay, there is a symmetric part which is nabla I, Aij, nabla I, you recognize, nabla J, right? Recognize it? Aij, okay. Aij, A, okay, Aij x is Aj x, so an x-dependent coefficient, and ax is a positive, strictly positive, larger than this S star times identity matrix. I have, so this will give me the symmetric part of the diffusion, and I assume that the symmetric part is bounded below. That's the ellipticity. That's why we call it ellipticity condition. And I also have some Hij(x) equals H minus Ji x, right? About which I don't assume anything now, and I call that Vi x be sum over j dj hji. Right? So this is an anti-symmetric matrix, tensor, and its curl, actually it looks like a divergence, but actually it's a curl, it's a rotation due to the anti-symmetry and all that. Its rotation gives the vector field, the drift field, right? And the drift field is divergence free. From here it follows that this is divergence free, right? And my diffusion, first the infinitesimal generator of the diffusion will be, maybe I put a 1/2 sum over Ij, right? Plus sum over j v sub j dot. But this is the same, and this is what they call in PDE, put it in divergence form. In divergence form, this is 1/2 sum over Ij nabla I Aij nabla j plus a 1/2, put a 1/2, maybe I missed somewhere a 1/2, formally the same Ij nabla I Hij nabla j. And due to the all symmetries, you will see that this gives exactly the same thing. So this is an infinitesimal generator, a diffusion generator in what it is called in the jargon of PDE, put in divergence form. Yeah?
Are you not missing one relation, one antisymmetric relation about the H?
Didn't I say that?
It should be antisymmetric.
It's anti-symmetric, didn't I?
In the 2D case,
It's written that it's anti-symmetric.
well, there is a minus sign.
This is a minus.
But in the 2D case, you will have a truly antisymmetric two-by matrix.
But this is it, isn't it?
Well, that doesn't tell you that it vanishes on the boundary, on the diagonal.
If it's anti-symmetric, if Hij minus, sorry. Yeah, sorry, thank you. Yeah. No, sorry, this is it. No minus. It was nonsense. The minus was on the the minus was on the wrong place. Sorry, you are absolutely right. The minus was on the wrong place. That didn't make sense. Minus I doesn't make sense. Right? Good. Thank you. No, this is what I meant. Of course, this is what I meant. And that's when it's all true what I'm saying. Now I don't want to erase Nash's theorem before. This corresponds to a diffusion.
Another question related to the earlier guy. You have a choice about H.
Yeah, it's not unique.
And then in your condition, because actually your conclusion is only about the random walk, so it does not directly depend on the choice.
But I must have a choice of H which is bounded. Or I must have a choice of H which is L2.
And it's not because you have one choice for which is bounded or L2 that the other choices will be bounded or L2. That's correct.
I didn't understand what you were saying, sir.
You have to make the right choice. If you want
In the random case, in the translation invariant random case, the way I construct it is exactly what they call the Coulomb gauge.
and for that one, you will check your position.
Yeah.
But if you
You can do it worse. You can do something wrong. You choose the bad H, and you don't get the bound. But otherwise, the bound exists because with a good choice of H, it exists. Just you can't prove it if you choose the wrong choice.
That's correct.
The wrong.
And the choice that you're going to make is the optimal one. You know that.
The choice I made actually for the random case. I'm interested only in the translation invariant ergodic random case. I didn't spell out all details because you know time how fast goes, but I told you if you look at the paper, that paper with Cosma, there is a chapter in that about the construction of this object. It's nothing new in it because if you want, it goes back to 19th century mathematics. But it's good to settle. Indeed, the choice in the L2 case, it's a construction in the Hilbert space with those operators I defined and so on. And it's a convergent construction, so it's a valid construction in the Hilbert space, and the result is exactly what otherwise it's called the Coulomb gauge.
Which is the optimal one?
Which is the canonically best one, usually. And for my case, the optimal one. Now let me just write down this diffusion and then come back to Nash's theorem to prove. This is a good question you asked because indeed otherwise things are so abstract. Now the diffusion, in this case, the diffusion will be dxt will be, let me put it this way, axt dbt plus probably I should put here like this gradient of a x. This is a vector. This means so you push this on the other side, and otherwise you get a vector field if you apply this sum over I, nabla I, aij, plus v, not of x, but of xt, this is the diffusion. So here is the probabilistic interpretation. In continuum. In the lattice, it's the same, just in the lattice you use different indices. And good? Did I answer your question? Yes. Yeah, good. Okay, so let's prove Nash's moment bound because that's indeed beautiful. May I erase this? Yeah. Yeah. I introduce some notation. I'm in the Nash context, so this is deterministically given V's for the moment, right? I introduce some notation. I will denote by PTX as I let my random walk starting from 0 is probability starting from the origin that xt is at site x, right? I denote MT be expected value for the random, this means random walk starts from the origin of the lattice, absolute value of xt, which is sum over x in zd, absolute value of x ptx. Straightforward. And I denote by ht, and this is the ingenious part of it, the entropy of this measure, of this probability measure. So this will be minus probably, yes, sum over x in zd of ptx log ptx. This is the entropy of the distribution, right? And I will prove 3 lemmas. So now I start the proof. Lemma 1 is the following. I'm in this context, so I don't have to wait till a long time because I have an absolute upper bound. I have an upper bound for these values. So I say that for any t, if mt is larger than 1, of course, I'm curious, I'm interested in mt really large, so in the first 2 seconds it will be less than 1, but let's assume it's larger than 1. Then it is the case, okay, should I put it? There exists a constant, there exists a constant C1 depending small c1 only on the dimension which is positive, such that for if mt is larger than 1, then I have this lower bound, then mt by force is larger than or equal to c1 times e to the ht divided by d. I'm sorry if I make t down and t as a variable is the same. So there is a lower bound for mt in terms of the exponential of the entropy divided by dimension. It's you misbelieve or something. It's not an intuitively very straightforward thing. It's a very beautiful thing, and it relies on the entropy inequality, which I will prove in a moment. I mean, I will prove this one based on entropy inequality. Actually, what I'm saying, this lemma 1 is a direct consequence of the entropy inequality, and actually it's valid for any distribution. It's not about pt here. Take any distribution on zd and the same thing holds. So t is not involved here, right? This is lemma 1. Lemma 2, I will prove it. Lemma 2 is the following. There exists another constant, C2, this is capital C, it will be, this C is important that it's positive, it's a lower bound, the next one will appear in an upper bound, so, which depends only on the dimension and S lower starred, such that for any t positive, strictly positive say, it is the case that ht divided by d is larger than half log t plus minus this constant. So there is a negative constant such that ht divided by d is larger than logarithmically increasing from there. Right? Of course, ht is always positive, so this doesn't say to you anything when I could say the positive part of this. Right? And if you think a little bit, this is nothing else but the previous Nash inequality, not the Nash inequality, but the heat kernel diagonal upper bound. If you will see, from the heat kernel diagonal upper bound, this just drops out. Right? Now, if this is the case, then it is true that if I subtract from ht, let me see, if I subtract these guys all together, I get something positive. That's the same thing. So let me denote, let gt be just the same thing. So ht divided by d minus half, not half, yeah, d is there, okay. Half log t plus C2 is just ht shifted. And I know that this is non-negative. This is the same thing. Right? And in terms of this g and this lemma, so then lemma 1 becomes, then lemma 1 let me put a, because it's just transcription of lemma 1, using, you see here you have an ht divided by d. I rewrite it in terms of gt because it will give me more explicit thing. In lemma 1 reads like t to the minus 1/2 mt is larger than or equal to a c3 times e to the gt. This is exactly the same thing. If I insert for g, you insert, sorry, for h, you insert this expression of g, that means g plus as you have to, then you get exactly that thing. It's nothing else. And g is positive, c3 is expressed in terms of c2 and c1. And the last lemma lemma 3, this is the most, maybe the most difficult one. There exists a constant which I will call C4, which depends now in everything. It depends on dimension, it depends on S lower, on S upper, and on H upper, such that for any t, yes, say for any t positive, it is true that square root of t, 1 over square root of t, so t to the minus 1/2 mt is, here you see the, so far you only saw upper bound, lower bounds for mt, but we want an upper bound. Right? Now this will be an upper bound. This will be less than this C4 times gt plus 1. Right? Now I will prove these three lemmas, but let me close the theorem first. If I have these three, actually if I have this one and that one, then I have the theorem. Why? Because this square root of mt, mt over square root of t is bounded above by a constant times g, and bounded below by a constant times exponential of g. It can't be too big. Right? You have a linear function, you have a linear function plus 1, and you have an exponential function with another constant. So these are constants here. So you have a linear function, and you have an exponential function, and this is a lower bound, that's an upper bound, so this is your upper bound for mt by square root of t. Is it clear? Question? No question. This is so simple. Yeah. Now let's no, it's simple. Once you have these lemmas, it's indeed simple. Let's prove the lemmas. Let's prove the lemmas. Let me do lemma 2 first, then I can erase it because that's indeed simplest. That's indeed nothing else but lemma 2, proof of lemma 2. Lemma 2. We know, this is, I shouldn't even write it down because we know from the Nash inequality, which was the previous stuff, we know that ptx for all x is less than or equal to some constant, which is called c5, whatever, c times t to the minus d half. Right? Then insert it in the definition of the, in log pt, you get this thing. Yeah? Straightforward. Any question about this? So this is just straightforward consequence of our previous heat kernel diagonal upper bound. Any question? Anybody understands this? Everybody understands this. Good. So this is done, and I can erase, at least I can save that much space on the blackboard. That much space on the blackboard. Now, about lemma 1. For lemma 1, first of all, note the following, and this is another message to take home for those who don't know entropy, because entropy is a paramountly important thing. Let V be a countable set, entropy inequality. And this is again something terribly important in all contexts, not only in my context, everywhere. Let V be a countable set. In our case, this will be ZD, finite or countable set. Let P be a probability distribution. Let Px a probability distribution on V. And define HP, define the entropy as I defined it. HP be the entropy of P, be minus sum over x in V, Px log Px. By log, I always mean natural logarithm. Otherwise, you have to change some constants. Right? So this is the entropy of the distribution. And now the statement, the entropy inequality is an important theorem. Entropy inequality, right? The entropy inequality is an important theorem. It is the case that HP is equal to the infimum over all functions f defined on V. F is defined on V of logarithm of sum over x in V of e to the minus fx plus sum over x in V of px fx. What is the point here? You have an unknown measure, you want an unknown probability measure, you want to understand this p is there, but you don't know it well. On the other hand, you have the counting measure you understand perfectly well, right? And what this inequality tells you, it relates the expectation of your function with respect to the unknown measure with the logarithm of the exponential moment with respect to the known measure. And the entropy inequality tells you that actually HP entropy is the infimum. And from here you can play various things. So from here you can play, so that means that entropy is larger than or equal to this expression. Always play with it, right? Now, homework for you. First, prove this. It's a simple, it's not difficult. Prove it for finite. I'm happy if you prove it for finite set. It's a variational problem, right? It's a variational problem. You have to. It's elementary analysis, and prove that it's attained. So the infimum is attained by fx equals, let me not make mistakes, minus log px. Mind, you can add constants. If you add a constant to your function, nothing is changed. Here you add a constant that comes down additively by the logarithm and with a negative sign and with a positive. So you can add a constant. Constants don't matter. Right? Now, you will find what I'm claiming, that this inequality follows from the entropy inequality directly. It's a direct consequence of the entropy inequality. As time is running out, all details are here in a half page. All details are here in the so in the next half page. It just tells you, oh no, one more thing I tell you, and then I don't give the rest of the proof. Namely, use the another note. Okay, apply, I proved Lemma 1 now. Apply the entropy inequality with V equals Zx, Zd. Px, of course, is Pt t of x, and choose the function, let me see, and choose the function fx be absolute value of x. Mind, if you take absolute value of x, you have to compute s times at the constant s, at the multiplicative factor here s. S is a positive multiplicative factor. With s positive. Then the exponential sum will be finite, of course. And note that, okay, and apply all, and one note that for s, note that for s less than or equal to 1, you have the following inequality. You have sum over x in zd of absolute value x, e to the minus s times absolute value x is bounded above by a constant times s to the minus t. This is an elementary, reduce it to integrals and do some elementary. This is elementary. This is true. Put these things together, you get this inequality. Good? So the first lemma is, I consider the first lemma proved. The second lemma is proved. Go to the third lemma. That's the most interesting part. Actually, no. The entropy inequality is very interesting in my opinion, but less surprising maybe. We have used lemma 1 prime has been used already. No, I didn't prove lemma 3. Yes, sure. Lemma 3 is there. And I prove now lemma 3. Mind G. I will erase now G, but mind that we will use G. Of course, it appears somewhere there. Good. Now, in order to prove lemma 3, note that I will prove soon, will prove two inequalities. The one is about ht dot. By the way, ht dot, you have a Markov chain, a continuous time Markov process, and you have its entropy. I mean entropy of the distribution after time t. This will be monotone. In this case, it will be monotone increasing. Its derivative is larger than or equal to some constant, which is depending only on dimension, and s lower bound times sum over x in zd, sum over k in E, and I have something like pt x plus k minus ptx. It's no good space-wise. Okay, it will be good. By pt x plus k plus ptx times ptx squared. Actually, what you see here is the following. This is sort of, for those of you who know some entropy theory, this sort of Fisher entropy. So this is the gradient. So I say that the rate of change of the entropy is bounded above by the average, because it's averaged out according to the distribution of the gradient of the distribution divided by, okay, this is the gradient of the logarithm of the distribution squared. This is the gradient of the logarithm of p, because you have a 1 over p times gradient of p squared. Gradient of the logarithm of the distribution squared averaged out gives a lower bound on the rate of increase of entropy. This is a Fisher type of object. Sometimes they call it Fisher entropy, but actually this is not an entropy, it's an entropy rate. Let me call this bound 1 I'm going to prove. And I'm going to prove a second bound, which is 2, for mt dot, I have to put here absolute value because this doesn't have a sign. There is less than or equal than a constant which depends only on d, on dimension. Yes, I have similarly a sum over x in zd, sum over k in e, which means sum over edges of the lattice. Yes, I have s sub k x plus sum over L in E, absolute value of H sub K and L x. Right? Times the same expression as there, PTX plus K, minus PTX by PTX plus K plus PTX, absolute value, PTX. I will prove this in a moment. I mean, I will sketch or I will tell you how to prove it. I will not spell out all details because it's standard steps, right? Question? There is no square. You will see a square in a moment when we apply Schwartz. There is no square here, right? And this is less than or equal to, of course. So let me call this A, 2A. And this is less than or equal to 2b. Mind that I have upper bounds for these guys. So I have some constant times, which depends only on dimension, which might be different of this constant, might be d times that or d squared times that something. You have an s upper starred, and you have an h upper starred, and you have sum over x in zd, sum over k in e. You have, let me put here like Laplace gradient p by p, which means this. This is a gradient by p, right? I just spared time. And now you will see, of course, the square. So by Schwartz, we see what? We see that, let's see, what do we see by Schwartz? Yeah, anyway, it's empty is m bar t. So this summation, you have a s, here is the summation. Just apply Schwartz and you get, because this is a probability measure, if you apply Schwartz, you get this upper bound, you get some other constants, you get some constant. Just let me see. Why do I have this depended only on lower, this depended only on the upper. Oh no, this depended on the yes, so this depends also on the upper, good. So this is less than or equal to some constant which depends on lower, upper times h dot t to the 1 divided by t, divided by dimension for convenience, to the 1/2. You agree? So this is a simple Schwartz. I put here the d because I will need it, but this is just a simple Schwartz inequality, right? Which is Yes, which is, this thing is equal to C times, this C times h dot t. Okay, if you go to the definition of G, you will see there was a logarithm in the G, but when you take the derivative, the logarithm of the derivative of the logarithm will be 1 over d. So what you get, if you check, what you get is G dot dt plus 1 over 2t to the 1/2. So this is what we got. So here I just inserted, I prefer G, you will see G is positive. It will play a role in a partial integration in a moment that G is positive. Good? So I'm almost done. I'm almost done. Now I integrate. I integrate. I integrate this inequality. If I integrate this inequality, I get absolute value of mt is less than m0 is 0. I start from the origin. So I integrate this guy less than, let's see what we get. Okay, let me write it less than integral from 0 to t of absolute value of m dot u du, of course, because it's just a triangle inequality, which is less than integral from 0 to t of, I have a constant here of, let me see, I write 1 over square root of 2u times 1 plus 2u times g dot u to the 1/2 du. And I do some integration by parts. I will not repeat these computations. You have, the rest is straightforward integration by part, and at a point using the fact that g is positive. So you do integration by parts here, and at a point you have a term which you neglect. Let me not write it down. If you go to page, I don't know, page 22 of these handwritten notes, you find all the rest is integration by parts. So if you do all that, in the end you get, this is less than constant, you get a square root of t from integration by parts of this guy, and you get a gt plus 1. And we are done. Time is running, and I don't want to waste time with integration by parts. Right? So what the ingenious things are is that put together entropy inequality and the clever choice of bounding. Okay, entropy inequality, entropy increase rate, which is well known, but noting that the m moment increase rate is something very similar. Right? Now, how do you get these two things? As time is running, probably I will not give details, but these two things are more or less standard. Namely, you have to use the following very simple thing, namely that ptx dot, that's the time change, the time derivative, time increase of the distribution, is, just write it down. It's the adjoint generator acting on pt. So I write it down explicitly. Sum over k in E S sub kx ptx plus k minus ptx minus sum over k in E v sub kx ptx plus k minus ptx. This is just the adjoint generator acting on pt. Right? Now, go to the definition of which is expressed in terms of P, and put in whatever, so put in this expression and massage it. When I say massage it, I mean that you have symmetries of this guy and you have symmetries of this guy. And you have to use, when partial summation and so on, you have to cleverly use this. On the other hand, when you do, you see, in this you don't have the H appearing, only the, not even the V, but this massaging and all that. Here the H appeared. If you go to page, I'm not going to do this computation on the blackboard because it's just not instructive, I'm afraid. Probably page 24 of the handwritten note. No, yes, bottom of page 24. By the way, okay, there will be one more remark. In page 24, it starts the computation of this m. Again, you have an expression of m. There was this expression, absolute sum of absolute value of x px. Time derivative, insert this expression and start to massage it and replace s sub k by its expression with h. Use the symmetries of h in some summation by parts. You do it yourself, you gain much more than if I do this type of things at the blackboard. And you get what you need. Good? So I'm not going to give details. All the computations actually, trust me, are simpler formally, shorter at least, less to write, if you do it in continuum. For those of you who are better used with Laplacians, gradients, curves, and so on in the continuum, do the analogous thing in the continuum. We will have, it's fun to do it, and you will understand exactly what's going on. In the remaining time, I want to show you what is the difference, what do I do which improves on this. So how to go, so let's assume now so assume that skx is actually sk tau omega. I erased what I didn't want to. That was a mistake. Tau x omega and vkx equals vk tau x omega. And what is assumed that these are ergodic. These are ergodic and L2 plus epsilon. No, I mean HKLX is HKL tau x omega, and these are L2 plus epsilon, right? Note that the upper bound was used only in the third lemma. So lemma 1 and lemma 2 go through exactly as lemma 1 and 2 unchanged. Right? And lemma 3, in lemma 3 I have to do something, and that's what I'm going to show you now. That's what I'm going to show you now. Second. So I had this expression 2a. The expression 2a was the following, and I have to write it down again. I had this thing. I had m dot u was bounded from above by some constant, and this constant depended only on dimension and the lower bound, depending on dimension and s lower, times, and I write again what was on the blackboard, I have sum over x k sk x plus sum over bounded from below, yes, sum over L in E absolute value HKLX. This was on the blackboard, just unfortunately I erased it. Times I had a PU x plus k minus pux by pu x plus k plus pux times pux, if I'm not mistaken, right? Now, I do the following. I integrate this inequality, I integrate now with respect to time rather than integrate at the end as Nash did. So I integrate with respect to time. I integrate this inequality altogether. I integrate from 0 to t. And I also apply some Hölder inequality, as I show you now. Namely, I get from here empty, I just sketch what I'm doing because again it's very computational and maybe you don't like it very much. What I get is this is less than or equal to. I have a constant, I apply a Hölder, namely I raise this guy to a power 2 plus epsilon, and this guy to another power which is corresponding to the 2 plus epsilon, you will see. I have, the computations are correctly done. If they are correctly done, I have t to the 1 over 2 plus epsilon. It's easy to make mistake now. 2 plus epsilon. I have 1 over t integral from 0 to t of sum over x and k of skx plus sum over L, absolute value HLKX to the power 2 plus epsilon. 2 plus epsilon. Sorry, is it correct? Yes. I have a PUX. And I have a dt. These are all there. So the Hölder is done with respect to this sum and the integration. The sum and this sum and the integration are Höldered, if you wish. And I have another one which is integral. Altogether this guy. Altogether, I would follow better what Hugo did. So altogether this guy to some power which is 1 over 2 plus epsilon. Right, and I have another one. Which will be integral from 0 to t sum over x and k of, let me write it shortly as it was, Laplace or gradient of p divided by p to the power 2 plus epsilon over 1 plus epsilon and p ux and dt, and altogether this guy to the power 1 plus epsilon over 2 plus epsilon. Now what you see, this second thing is similar to what was previously in Nash's theorem, just integrated with respect to time. I separated the first one, and what I note is the following, that this is an ergodic average. The integral over time, mind, this is the distribution of my random walk in random environment, and I sum over x and k, I sum over the positions. So namely, I average over, so what you see with the blue, what you see inside the blue stuff is equal to 1 over t expected value, quenched expected value of integral from 0 to t of sum over k s sub k at tau x u omega plus sum over L, absolute value, H sub k and L at the same point. Probably, sorry, du. So it's an ergodic average over the trajectory of my environment as seen from the Landon Walker, which is an ergodic Markov process. So this average, due to the, okay, not to the standard ergodic theorem, but what is called, how is it called, Chacon-Ornstein. Due to the Chacon-Ornstein ergodic theorem, this expression, what I call blue, due to Chacon-Ornstein, sorry, some 2 plus a power 2 plus epsilon is missing. Yeah? There is a power 2 plus epsilon here. So the blue stuff, what you see down there, so this ergodic average converges almost surely for almost all alpha, almost surely for almost all omegas, converges to what? To integral on omega of that sum over k sk omega plus sum over L hkl omega all together to the power 2 plus epsilon d pi omega. That's ergodic theorem. It's a bit of a sophisticated ergodic theorem, but it's the ergodic theorem. Hence, it follows that this can be replaced for sufficiently late time. This can be replaced by, say, twice that constant. And the rest goes exactly as in Nash with other exponents. You have to, the rest is computational, something like in Nash. Is it more or less clear what I've done? Pierre, is it more or less clear what I've done?
Yeah, what would go wrong if you would take excitement to be 0?
Then in all this stuff, if I go to the end, I will get a term. Let me recall. I have to look at the detail now because there is a term 1 over epsilon somewhere. Yeah, so when you have to integrate, you have these things here to, okay, the other term which you compare with the entropy increase. And when you integrate, you will get a term from here somewhere. You will get, when you integrate according to time, you will get a term 1 over epsilon.
You just said epsilon to be 0, then you get the integral of the derivative of the entropy.
That's right, but mind that that's not sufficient because why? Because give me a second. For some reason, I can't recall now, but there is, when you do the computations properly and you compare things you compare this guy with what you don't see anymore with the entropy increase, then you say formally this gives you exactly the entropy, but that somehow is no good. That somehow is no good. Let me not tell you now because I don't remember now at which point of the computation a 1 over epsilon drops out. So formally it looks like good, but you get a 1 over epsilon in a term, and that doesn't help. Okay, I come back to, I wouldn't be able now to put my hand, because when you integrate, then the 1 over epsilon comes in.
No, actually, I guess you would get an inequality like n is bounded by h. We just go with that's not exactly what you wanted. What you wanted was the entropy minus log of t.
Yes.
So maybe you missed this log t term.
Okay, let me this postpone now because I wouldn't find the epsilon now. Otherwise, for the rest, okay, I asked Pierre because he's the person who will understand best, but others in the class, did you catch something about, more or less? More or less. So anyway, the point is that it can be extended and it gives a little bit more. I still have few minutes left. How much do I have left? Sorry?
Yes,
few minutes. Then I don't do any more mathematics now. Tomorrow I will finish, or when I'm next coming, I will finish the quenched, because this is needed for, okay, why do I need this? I need this because I mean the moment bound, I need, mind that this theorem gives you a moment bound for almost all omegas, almost all environments. The moment bounds which I have from the previous theorem is annealed. It's averaged over the environment and it's not sufficient for the quenched central limit theorem to be proved. So this will be the starting point, and there are some other parts to be used, but somebody told me some days ago that, and I don't know what Asaf is here because he told me, that whenever you give a lecture, you must say what? One joke and one proof. There was no complete proof. All proofs were sketchy. I'm not able to tell you jokes. I will not tell you jokes, but I will tell you instead of jokes two things. First of all, I want to quote something from Nash's paper, which I love to quote. If I can open the paper, here it is. This is a paper written by one of the great mathematicians of our time, or not your time, but my time. And not even my time, I was barely born when this paper was published. But anyway, it's a wonder. It's a central paper of 20th century mathematics. I think many of you will agree. In the introduction, I quote from the introduction of the paper 2 sentences. He says the following, after he exposes what's done in the paper. He says, the methods used here were inspired by physical intuition, but the ritual of mathematical exposition tends to hide this natural basis. So let me do it again. The methods used here were inspired by physical intuition, but the ritual of mathematical exposition tends to hide this natural basis. This is a warning for all of us. So there are natural questions, there are natural objects in mathematics we deal with, and we are pushed towards this abstraction and speak in very abstract terms, and this ritual of mathematical exposition, I think, is very beautiful. Another thing which I want to show instead of a joke is you are young people here, most of you, asking for letters of recommendation and looking for jobs, right? All of you, either jobs or postdoc positions and so on. And you ask letters from your professors and mentors, don't you? And you think that the long letters are the best letters. The long letters, which tells in detail or what this clever and very good guy or girl did, and so on. You know what I'm going to say?
Yes.
Okay. I will read you the letter. So John Nash, in 1948, applied for a PhD position in Princeton. He's got his undergraduate degree from Carnegie Mellon, which was at that time, it was not yet a university anyway. And he had a mentor there who was Richard Duffin, who was a famous person in Fourier analysis at that time. And he applied to Princeton, where Solomon Lefschetz, who was one of the big analysts of the time, I don't know whether he applied to be a PhD student of Lefschetz, or Lefschetz was in charge with the PhD admissions in Princeton. Anyway, so here's the letter. What Richard Duffin, who was a well-established Fourier analyst at that time, wrote. Dear Professor Lefschetz, this is to recommend Mr. John F. Nash, Jr., who has applied for entrance to the graduate college at Princeton. Mr. Nash is 19 years old and is graduating from Carnegie Technical College, I think, in June. He is a mathematical genius. Yours sincerely, Richard Duffin. That's the letter. You can. Okay, see you tomorrow.